Okay, guys, so this is part 2 of hopefully 2. We'll see how far we get with it. Might have to go into a 3-part video, and there's quite a lot to cover here. So this is just takes place after page 5 of the notes. We're finished with Boyle's law. We're not going to touch on gravity. This is important because it feeds into circular motion that you'll be doing in the next topic, and then into Hooke's law from there. So this bit is a little bit confusing. Well, it's not actually. Personally, I think it's not too hard. Some people find it very confusing to deal with, but it's generally okay. It does come up as kind of its own question, so it's not that bad to get. So we're back again to looking at a Newton law. So what is Newton's law of gravitational? It is that any 2 point masses in the universe attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. That is an insanely long, confusing definition. That is why I tell people, use this. This is in the log tables. Fg equals g m1 m2 over d squared. G is the universal gravitational constant, m is the mass of the object, d is the distance, and f is the force of gravity. It's the exact same thing, you see? States that, oops, pen's dying, any two universes, there we go. Any 2 point masses in the universe attract each other. Any 2 point masses attract each other. Gravity is directly proportional to the product of their masses. The product, that's the two multiplied together. F is directly proportional because they're on this above the line. Inverse proportional to the square of the distance. There you go. The square of the distance between them. It's inverse, so it's below the line. You see? So it's all related. Okay, they're the same thing. Things to note: gravity is always positive. Okay, the size of the force on each mass is the same. In other words, the force of gravity that the sun experiences on the earth is the same as the force of gravity the earth experiences on the sun. Okay, the universal gravitational constant is there. It's in your log tables, but they'll generally give it to you 6.7 by 10 to the minus 11. You don't need to learn that off. It's in the log tables, and they generally give it to you. Okay, the SI unit for G is Newton meters squared kg to the minus 2, which of course tells you how to rearrange the equation if you're asked to find it, but they never really do give it to you. Okay. And then just general gravity stuff, which is you should really know. Anyway, okay, so problem 9. Find the gravitational attraction between two steel spheres, each of a mass. So M1, M2 is 1 kg, 1 kg. When the distance between their centers, so D is equal to 1 meter. And the gravitational constant, guys, I'm not going to write it up because it's there given to us, okay? So in each of these, I'm not going to write this number out each time because it's a pain. It's there, it's given to you. In your exams, I would write it in, so you don't forget it's there. But for just for the sake of time on this thing, I'm just going to move on, okay? So F equals G M1 M2 over D squared. Fire in all your values, put it into the calculator, and we should get 6.7 by 10 to the minus 11 SI unit, newtons. All forces are newtons. Okay, so problem 10 then. Find the gravitational attraction between the Earth and the Moon. The distance from the center of the Earth to the center of the Moon is 3.8 by 10 to the 8. So, find the gravitational attraction between the Earth and the Moon. Okay, I forgot to put in. So I took these out of the book Real World Physics. That's where most of the information is I'm getting it from. So the questions are coming from that book. So they give us the mass of the Earth, because obviously I couldn't answer this without this bit of information, is 6 by 10 to the 24 kgs. And the mass of the Moon was given to us as 7 by 10 to the 22 kgs. And I think that is it. Right, so again, we have, what do we have? We have distance given to us. We have mass of object 1, mass of object 2, and we know the gravitational constant. So F equals G M1 M2 over D squared. Fire in your values, guys, into the calculator, and you should get 1.95 by 10 to the 20 newtons. There you go. All right, so gravity and weight, we kind of touched on this before. You definitely did it in junior cert, you've probably forgotten, but we've touched on it a little bit before as well. So weight is basically mass times acceleration due to gravity. W equals mg. It's pretty much the same as F equals ma all forces are the same, so force equals weight, and you're basically accelerating at the speed of gravity, hence why F equals ma is the same as W equals mg. It's just different symbols, same thing really. So you have to convert your weight, if you want to get the weight of something, you convert it into this, okay? All right? So so here, this is not a derivation, but it can be handy to know. Let me see now. At the end page 56 locked. I think this is, so this is where this equation comes from. G equals gm over d squared. I don't think I've ever seen it getting asked, but it could get asked, I suppose. Basically, what you say is that weight equals mass times gravity is the same as force equals mass times gravity. Okay? So therefore, if F equals gm up, then mg equals the 2, m cancels m, and that's where you get g equals gm over d squared. That's basically it. That's all it is. Okay? Force is equal to mass times gravity, so you can slot it in. All right, but it's in the log tables. But just in case they ask you how to do it, that's all it is. You simply say weight equals mass times gravity, which is that. F also equals that. The two equal each other. G's cancel, or m's cancel, so g equals gm over d squared. That's it. The problem with this is, I will say to people, is don't get the two g's mixed up. That's acceleration due to gravity. That's the gravitational constant. Don't get them mixed up. Okay, it can happen. Okay, so this is basically 3 questions now, and that's the end of gravity. The last one is a past example per question. It's a difficult one. I often go through it just to kind of show you how to approach it. So the mass of the Earth is, let me check my notes there, is it the same as the previous question? Yeah, so the mass of the Earth is the same. So I'm not going to rewrite it out. I don't rewrite out a lot of these because there's numbers. These are large numbers, and I don't have space on the notes. So the extra bit of information we get now is the radius of the Earth. Everything else is the same as the previous question. Is 6.4 10 to the 6 meters. Yeah, everything else is the same. So find the value of acceleration due to gravity on Jupiter, given that the radius of Jupiter is, so radius of Jupiter is that, and the mass of Jupiter is that. Hence find the weight of a 90 kg man on Jupiter. Okay, so in other words, we got to find G, and we know that G equals gm over d squared. Okay, so we have the gravitational constant, we have the mass of Jupiter, this is m, and this is d. Okay, so basically the d, I meant to cover that actually, now that I'm reminding myself. So when we're doing this, we're trying to find the force of gravity, attraction. You go from the center of the planet to the center of the planet. That's your distance. I meant to cover that. All right, so it's always from the center of the planet to the center of the planet, not from the surface, the center. Okay, so the distance, the force of gravity felt between Earth and the Sun is from the center of the Sun to the center of the Earth. So that's why here, when they gave us the radius of Jupiter, the radius is the distance, the surface of the planet to the center of the planet. So that's why we put that in there. And when you put that into your calculator, you should get 25.98 meters per second to the minus 2. Okay? And in the second part, W equals mg, which equals 90 times 25.98, which should give us 2,338.2 newtons. Okay, there you go. All right, problem 12. Find the acceleration due to gravity 100 kilometers above the Earth's surface. Okay, so again, gm over d squared. Okay, so we have the radius of the Earth. I gave it to us there at the start. Radius of the Earth is 6.4 by 10 to the 6. So if we're 100 kilometers off the surface of the Earth, d now changes to the radius of the Earth plus 100 kilometers. Okay, you see, that's what's happening there. So therefore, this becomes G equals gravitational constant, mass of the Earth from the previous question before, times 6.4 by 10 to the 6 add 100. Oh, we got to convert kilometers to meters. So what do we do? Multiply by 1,000 meters. So when you fire all that into the calculator, we should end up with 9.5 0.51 meters per second to the minus 2. Where am I getting the mass of the Earth? Not from this question, I mean back here. 6 by 10 to the 24. Okay? All right. That's usually given to you in the question anyway, unless they ask you to find it. All right, so the last one here now, this is going to take a bit of time, and then we're on to turn-in effect and moments. So describe how the weight of an object changes as it moves from the surface of the Earth. So this came up in 2000 and what year did I have this down now? 2010. Okay. All right. So describe how the weight of an object changes as it moves from the surface of the Earth to the surface of the Moon. At what point between them is the resulting gravitational force on an object zero? And where is that? Okay. So what you say there for the first part, I'm not going to write it out. I'm just going to explain it to you over the video. So how does the weight change? So as you move from the Earth to the Moon, you get lighter and lighter and lighter and lighter. Okay. Until the force of gravity gets to the point of zero. Why? At that point, the force of gravity, the gravitational pull of the Earth equals the gravitational pull of the Moon. Okay? And then the closer you get to the Moon, you start to gain your weight again because the gravitational pull of the Moon is getting greater because you're moving towards the Moon. That's it. Okay? So now the maths part. So this bit now, guys, it's going to be quite long, so I'm going to fill in the little, there's only a small page. All right, so in your notes, what I would advise you to do is divide this into 3 different things like this. Okay, so I'm going to try to squeeze it all in. You should be able to, but I might not be able to with the pen I'm using is a bit too large. Okay, so we start. And what information are we given? We're told, that the point where the gravitational force of the object is zero. So the gravitational force is zero. And distance between the Earth and the Moon is that. And the mass of the Earth is 81 times the mass of the Moon. So in other words, what do we know? All right. So how do we write that? So we can say distance of the Earth plus distance of the Moon equals 3 by 8.8 by 10 to the 8. You see? The distance between the Earth and the Moon. And the distances are center to center. So distance of the Earth plus the Moon is that. Mass of the Earth is 81 times mass of the Moon. So mass of the Earth equals 81 mass of the Moon. So there we go. That's the first bit, right? All right, so let's begin. We know the equation. I'm going to write this out, but you don't need to write this out. F equals G M M over D squared. Okay, so that's the same for both. That's for the Earth and the Moon. Okay, and F equals F. All right, which equals 0. All right, so therefore we can start here because it told us that F equals 0. Gravitational constant, mass of the Earth, mass of the second object, all over distance of the Earth, to be squared, equals G, mass of the Moon, mass of the second object, distance of the Moon, squared. Okay? Now, everything that's similar on both sides. We can get rid of gravitational constant, we cancel off gravitational constant. Mass of the two m's of the second object will knock each other out. So we're left with mass of the Earth over distance of the Earth equals mass of the Moon over distance of the Moon. So what we're going to do is, if we look over here, we have mass of the Earth is equal to 81 times mass of the Moon. Okay? Or, we rearrange that, 81 equals mass of the Earth over mass of the Moon. Alright? So we could do that here. Right? If we divide across by dE and divide down by mm. So mass of the Earth over mass of the Moon equals the distance of the Earth to be squared over the distance of the Moon to be squared. So therefore that becomes 81. Okay? This year when this came up, this is a horrible question. Okay? So what we can do now is we can square both sides, divide to get rid of the square. Okay? So root both sides. So get the square root of both sides. All right? In other words, we're going to get the square root of 81 and the square root of that. So that's going to leave us with 9 equals the distance of the Earth over the distance of the Moon. Do you see where I'm going to go with this? So the distance of the Earth is equal to 9 times the distance of the Moon. You see? So therefore, we set up here, distance of the Earth plus distance of the Moon is equal to 3.8. So therefore, 9 times the distance of the moon plus the distance of the moon equals 3.8 by 10 to the 8. So therefore, distance of the moon, that's going to be 10. 3.8 by 10 to the 8. So the distance from the moon, where all this equals 0, is 3.8 by 10 to the 7. And there you go. That's the answer. Okay? So F equals 0 when 3.8 by 10 to the 7 from the moon. There you go. That's it. Okay? So you have to read everything out, put it into a maths equation, compare it to, and break it down. Okay? So that was a horrible question when it came up that year. But it just kind of shows you how it operates. When you break it down into the maths, I always say break it down into the maths and it's a lot easier to follow. Okay? All right, let me see. Okay, so this is going to go over the 20 minutes as well. It'll probably run into close to half an hour, but I'm actually going to just keep going because it wouldn't be enough to make another video. All right, so we're on now to the last thing, turning effects of a force. Okay? This question rarely comes up. Okay, I've very rarely seen this question come up actually. Actually don't even remember it ever coming up in the Leaving Cert exam in a long question. It'll usually come up with question 12s in the parts of the questions. And that doesn't mean it won't come up, but just generally that's what it is. Not that difficult. We'll fly through it in 2 minutes here. So the turning effect is basically, okay, the moment of a force about the axis is equal to the magnitude of the force multiplied by the perpendicular distance. In other words, force by perpendicular distance. That's why if you have on cars, if you get a flat tire, you need the lever, okay, to take the nuts off. Usually it has a very long handle. That's because the longer the handle, that's the greater the perpendicular distance, which means you increase the force that you can put down on the nut to turn it, to get it to open. Okay, that's basically it. All right. Okay, so yeah, so generally what we do here is when we're determining it, you have what's called clockwise and anti-clockwise moments. Okay, down here. So the number of coplanar force acting on the body, clockwise direction, are given a different sign to those that rotate anti-clockwise. All right. So basically, if something turns it clockwise or anti-clockwise, you determine. I usually give clockwise plus, anti-clockwise minus. That's just my thing. Okay. You can do whatever you want. All right. Now you do need to know the following: the two laws of equilibrium, and I'll explain clockwise and anti-clockwise in a second. So the two laws of equilibrium are as followed. The sum of the forces in any direction is 0. In other words, forces up equals forces down. Second law, the sum of the moments about any point is 0. In other words, clockwise moments equals anti-clockwise moments. So what does that mean? That means if you have a wooden beam like this, forces up, things pulling it up are going to equal to the forces pushing it down. It's in equilibrium. The second law for it to be in equilibrium, so let's imagine that the point is the center point here. Okay, that's the center point. Clockwise is everything going to turn it clockwise, which means this way and this way. And anti-clockwise, we're going to give it a different color, is going to pull it this way and this way. You see? So if the clockwise, the red, equals the purple, you have it in equilibrium as well. Now, generally what I do to make it easier, I would advise everyone to do this. And I do it for the experiment as well. When you have your ruler, make the moment, the turning point, the 0 point of the ruler here. Therefore, your clockwise is everything that pulls it down, and your anti-clockwise is everything that pulls it up. That's basically it. It's much easier than trying to do it the other way, okay? Generally, they'll let you do it that way if you wish, but sometimes they can say moments above the 10 centimeter mark, in which case you have to do it there, and then you have to understand the ups and the downs, the clockwise, the anti-clockwise. Okay, right. So problem 14, 15, and that's it then. Okay, so these are actually, once you answer these two questions, you realize it's the same thing over and over and over. They're actually fairly straightforward. So I'm going to draw it out. I'll draw it out, kind of get it started, and then I'll have to probably rub out the drawing. So a uniform mass is 10 meters in length. So that's 10 meters. And a mass of 100 kgs is being carried horizontally. Okay. By a man and a boy. If the man is 3 meters from one end and the boy is at the far end, so we're going to put the boy here, and I'm going to have the man then here. That's 3. Find the upward force exerted by the boy and the man in the mast. Okay? And where should the man support the mast if he's to carry 3 times the weight of the boy? The boy remaining at one end. Okay. Right. So what I'm going to do is I'm going to say, because the boy is here, we're going to look at the moments about the boy. Okay? So if we look at the boy, what's the clockwise? The clockwise is going this way. What's the anti-clock? So that's clock. And this way is anti-clockwise. Okay? And what's the question? Sorry. Oops. We're looking at the forces up and forces down first. Marker rubbing all that out. Okay, so we have the forces up and we have the forces down. Okay, so if the force is up, so we have to get the force down first. So what's the force going down? That's the 100 kg bag. So we have to convert the 100 kgs into newtons. So the force down is 100 times 9.8, which is going to be 980 newtons. So now what we need to do is we need to discover the force of the man. So we know that because the man is about the boy, his distance, his perpendicular distance, is going to be 7 meters. All right, actually, hold on. Stall the ball there. I'm after making a big mistake. Okay, so let me rub that out. All right, so I forgot to mention something, and because I forgot to mention it to you, I forgot about it myself. The weight, okay, so the weight of any object, of the pole, okay, you experience that at the midpoint, at the halfway point. I forgot to mention that, and because I forgot to mention that, I made a big mistake there, okay? So the weight of the pole will always be experienced at the halfway point, okay? So therefore, the bag is 5 meters from the boy, okay? And then the man, because that makes more sense now, because I was going to end up with a crazy number. So the man is 3 meters from this end, which means the man is 7 meters from the boy, okay? There we go. So what we're looking for here is find the upward force exerted by the boy on the man on the mast. So the point at which we're turning, okay, is about the boy. So we're turning from the boy, all right? So our moment is force times distance from the boy. I was doing it straight up and down, and I said 10 by mistake. And that's what kind of threw me. I was wondering why it was such a large number. So therefore, all right, so boy is turning point. Okay, so the boy is the turning point. So we've determined that, okay? So therefore, what we'll say is down moment is going to be the force times distance. So the force is 100 times 9.8, okay, times the displacement, which is 5. You see? So that's going to give us 980 times 5, which is 49,000. No, 4,900. Yeah, 4,900. Okay? So 980 times 5 is 4,900. Going up then, our moment is the force of the man, which we don't know, so I'm just going to call F, times his distance, which is 7. Okay? So therefore, 7F is equal to 4,900. Why? Okay? Because it's horizontal, okay? And find the upper force. So we're assuming that it's in equilibrium. So it's carried horizontally, it's in equilibrium. So therefore, the man and the mast must be of equal weight. So therefore, 7F is equal to 4,900, which means F should end up being equal to 700 newtons. Okay? Find the upper force. So we now know what the man exerts. He exerts 700, okay? Now the weight of the beam, Okay, so we know the weight is 980. So therefore, the man is taking 700 of that, which means the boy is only taking 280 newtons. So the boy is only taking 280 newtons. Okay? That's the first one. That's my fault for confusing you with the first part. I forgot to mention that, and then because I forgot to mention it to you, I completely forgot it myself until I started the question and realized something wasn't right. Okay, now the second part is the more common of the questions. And there's a way to do this question. I think the very next question down is pretty much the exact same as the second part of this, and they all kind of repeat this kind of question, part 2. Okay? So I'm going to rub that out and rewrite it. So we have a mast. Mass is 10 meters in length. Okay? And we know there's 980 newtons of weight coming down. All right, so where should the man support the mast if he's to carry 3 times the weight of the boy remaining at one end? So we're going to make the boy, who is here, the turning point again. But this time we don't know where the man is. So we're going to call the distance from the boy to the man X. Okay, so we're going to call the distance from the boy to the man X. Okay, and yeah, and the distance from the weight of the beam to the boy is going to be 5. Just making sure I didn't make a mistake there. I'm correct now. I know I'm right. Okay, so the man has to support 3 times the weight of the boy. So we know that the force is down. Okay, so F down equals F up. So that means 980 is coming down. So therefore, 980 has to be pushed back up. All right? So if the man has to carry 3 times the weight of the boy, okay, that means the ratio has to be 3 is to 1. Okay? So therefore, the man has to, there's 4 parts. The man has to carry 3/4, and the boy would have to carry 1/4. So 3/4 would be 735 newtons, and 1/4 would be 245 newtons. Do you understand what happened there? The man has to carry 3 times the boy. So for every one of the boy, the man has to carry 3. So therefore, there are 4 parts, of which the man carries 3. So 3/4 of 980 gives 735. Okay? Now, we now know how much the man has to lift. So we know the force. F. Okay? So about the boy, okay, we know that down, anti-clock or clockwise, which is coming down, so clock equals the anti-clock. The clockwise is, of course, the beam coming this way, is force, which is 980, times distance, which is 5. The anti-clockwise is the man, whose force we said is 735, and his distance from the boy is x. So x equals 980 times 5 divided by 735. So x should work out to be 1 point, and it works out 6 continuous, so I just rounded it up in meters. In other words, the man would be no, my maths is wrong there. That's way too, because that'd be from the boy, which doesn't make sense. So let me rub that out. So we would have 980 times 5. I don't know where my maths is wrong there, but that's very wrong. Minus 735 divided by 735. There we go. Not 1.666. 6.667 meters from the boy. Okay, so my maths already was incorrect. I don't know where I got 1.66, but I noticed. Now the reason I paused there, how did I know that was wrong? Simple. My answer would have been that the man would have been 1.66 meters from the boy, which means the man would have been here, which would have made absolutely no sense. The beam would definitely fall over. Okay, so I knew straight away then that doesn't make sense. The man would have to be above the halfway point. So therefore, I just redid the maths again quick. Okay, so sometimes you'll notice it. If it works out that they're way too close together, that's wrong. You know straight away that's wrong. So just check your maths very quickly. Okay. Now the last bit here, a man and a boy hold opposite ends of a pole, 8 meters in length. So basically, very similar to that one that we just did. except slightly different, but it's the same thing. So there's a pole, it's 8 meters, the boy is at one end, and the man is at the other. Mass of 200 kgs is tied to the pole. Okay, so we have a mass of 200 kgs, so let me quickly fire that into the calculator. 200 times 9.8 will give us a value of 19,600. Nope, not 19,000, sorry, 1,960. So 1960, okay, is the weight in newtons. Now, the question is, if the man is to support 4 times as much as the boy, where along the pole must the weight be tied? Okay, so from the man to the object, we're going to call x. So if the man to the object is x, what's the boy? 8 minus x. It doesn't matter if you did it the other way around, you still get the same answer, okay? So the ratio here is what? 4 is to 1. So there are 5 parts, so the man was going to have to lift 4/5 of 1,960, which gives 1,568 newtons. And the boy has to just simply lift a fifth, so the boy will lift 392 newtons. Okay? Oops, there we go, yep. Okay, so this time, we're going to not be able to go about the boy, so we're going to go moments about the weight. So, moments about the weight are, both of them are pushing up, so our clockwise equals our anti-clockwise. So what's our clockwise? It's everything pulling down this way and up this way. So it's basically the boy. Okay, so clockwise is the weight that the boy has to hold, 392 times 8 minus x. And the anti-clockwise is going to be the man, because the man is pushing it that way. So that's going to be 1,568 times x. Right, so multiply this out. So we should end up on this side with 3136 minus 392x equals 1,568x. So I'm going to bring the x's to one side and leave the number on the other side. Okay, so bring all the x's to the other side, and when you bring them to the other side, you change the sign. So that becomes 3136 equals 1960x. So therefore we divide across, so x is equal to, we divide 1960 across, and we end up with x equals 1.6 meters. In other words, we position the bag 1.6 meters from the man and 6.4 meters from the boy. That's it. Done. That's all you ever do. You have the pole, you divide it in distance into x, pick a point to rotate about, and away you go. The last thing there I'm going to fire through. I know I'm close to well over half an hour now, but I just want to do this. Very easy, very rarely comes up. It'll come up as a short question. Basically with levers, they work about the point that rotates is the fulcrum, so the bit at which you rotate is the fulcrum. So if you have a lever on and a nut and you're turning the nut is the fulcrum, okay? The lever is used to exert the force, which is the load on the lever, and that's called the effort. What is a couple? A couple is a parallel forces which the same magnitude acting in opposite directions. In other words, kind of like if you have your steering wheel of a car, okay? That's a couple, okay? All right, same magnitude force, but acting in opposite directions, and the wheel will spin around, okay? And again, because it's a moment, it's simply the same as before, force times perpendicular distance. And again, to show it here, two forces of magnitude 40 act in opposite directions. If the perpendicular distance between the forces is 0.5, find the torque. Well, torque equals force times distance. Torque equals 40 times 0.5, which equals 20 Newton meters. Done. Okay, that's the end of part 2. Sorry, I went well over. I think it's close to 40 minutes now, actually. But that's that done. That's topic 9 done. I will get topic 10 up soon. Okay. If you have any questions on that, or if you spotted a max error, please do leave a comment in the comment section below, and I will try and get back to you as quick as possible.